I need you guys to remind me of sneezes in a minute. Okay. All right. So crest, trough, frequency, amplitude. Who wants to tell us about crest? Yeah. Top of a wave. So what do you mean by top of a wave? If this is a wave, tell me when I get to the crest. Or not.
You really did.
Oh, you couldn't see? I'll do it the other way. Whoa. Oh, middle. Okay. So middle of my line. That was good. Yeah, so crest is up here. All right. Trough, yeah.
It's like if you look at it as like two hills, it's a valley.
Okay, so the valley. Good.
Right there.
You could also call it a saddle. Like that's the saddle. You sit in the saddle anymore.
Yeah, I know.
Yeah, that's good. The valley, very good. Okay. All right. Now frequency, Amanda.
How fast or slow wave, like how rapid the waves go. Like this would be high frequency.
Compared to low, it's gonna be low. Okay, good. Yeah, it's how fast the wave is traveling past a certain point. Basically, how many waves travel past that point in a time frame. Like, okay, so how fast is this wave? Count in seconds. 1 1,000, 2 1,000, 3 1,000, maybe 1.5 waves per second, maybe, or maybe halfway per second. Okay, so that would be the frequency, how many waves pass. So if you're talking 8,000 hertz as a frequency, that means there's 8,000 waves passing per second. That's going to be a pretty high frequency. Okay, so frequency is the space between the waves and how fast they're moving past a certain point. Higher frequency equals what? More waves passing. If it's a sound, what does it mean? Higher frequency. What? No, not necessarily. What does higher frequency mean, guys? Show me higher frequency with your voice.
High pitch.
High pitch. Yeah, I heard it over here somewhere. Hey, Tristan, I'm a little suspicious with your hand on your phone like that.
I'll just hold it. I'll put it up.
So amplitude. Last one, amplitude. Height of a wave. So we're going to measure that this way. Amp. If you watch the Winter Games or the Winter Olympics or the Winter X Games, and they talk about a snowboarder getting amplitude, they're talking about how high they're getting out of the half pipe. So height of the wave is amplitude. Which one equals turning up the volume, frequency or amplitude?
Amplitude.
Yeah, amplitude. Okay, amplitude is going to make those waves bigger, so they hit your ears with stronger power, and therefore it's going to sound louder. Good. Okay, so let's see what else waves can do.
Know that you can't hear, but they're still there because these waves.
There are some sounds you can't hear. Elephants communicate with some sounds that we can't hear. They're too deep. Crazy.
Contain energy. And with enough din, you can make these waves do some incredible things. Outside of medical technology like ultrasound, one of the most commonly known ways to make sound do something is by breaking a glass. This works only when the sound wave is at the exact same frequency as the object you're shooting at. If you gently flick a wine glass with your fingernail, you will hear its frequency. Match that tone and turn the volume up, way up to like 11. That glass will break. Also within the range of hearing is sound levitation. This is way cooler than breaking stuff, if you ask me. Sound levitation has been around for years, but until recently, we couldn't do much with the stuff once it was levitated. It just sort of hung there in the air. Thanks to advances at a Swiss university called ETH Zurich, we can not only levitate stuff, but we can move it around, adjusting floating fluids. This works by using the energy in the sound waves. In this apparatus, the energy waves reflect back and forth so quickly they form what's called a standing wave, or a specific point where the energy from the sound can hold an object in midair. Think of it like these silly executive desk toys. The ball in the middle, that's the standing wave. The thing that they just figured out is how to move the stuff once it's levitated. Now they can use this system to manipulate liquids, combining and separating them, all without touching them with human hands, which is immediately applicable to drug manufacturing. Kind of cool. These energy waves can do a lot of other stuff too. The LRAD, or long-range acoustical device, is a weapon that shoots sound. It's like a sonic death ray without the death part. It can produce so much sound that you feel physical pain, like 160 decibels. That's loud. Think NASA rocket launch. But it won't kill you. It just really hurts, like a sonic hurt ray. If you combine some of those technologies, sound can produce really strange effects. In the 1950s, NASA and the US Navy built a device that produces ultra-low frequencies, or ultrasonic sound. If you pointed it at a person and set it to 19 hertz, people would have vision problems and get spots and stuff, because 19 hertz is the resonant frequency of the human eyeball. Kind of like that wine glass example we talked about. If you turn the volume up, people actually would have trouble breathing because the low frequencies were impacting the lungs like energy waves. And if you shot it through the ground, your skeleton would vibrate, causing nausea and joint pain. So which of these sound inventions is your favorite? The levitating ones for drug manufacturing, ultrasound, or maybe one of the ones that are used for evil? Share your thoughts with us, and we'll see you next time on DNews. Ways to make sound do something is by breaking.
Looks like a piece of plastic being wiggled.
Being a glass. This works only when the sound waves to make sound do something is by breaking a glass.
Okay, very good. All right, I need phones from Catherine and Addison in the bucket, please. All right, so now let's move on to the Doppler effect. Remember, look in the back of the book and see if you can find the page number the Doppler effect's on.
How late is down there? Sergeant?
Yeah, put it on this, just a science book. There you go.
Okay.
You don't want to put it in the bucket?
I'm getting my charger. I'm plugging it up somewhere. How do you check it if you're
Because you're staring at your desk.
What
Nobody
if I was just
stares at their.
pondering about something?
Really? Do you ponder about anything?
Yes, I do.
When?
All the time.
I got it.
Oh.
Just because it doesn't look like it. It looks like they're typing on your screen and everything. At least you didn't have to do it unreal with the
We always do.
standards project.
Oh, yeah.
I know, that's what Tristan does.
Surprises.
All right, so. Okay, write down on your paper a short description of the Doppler effect. Okay, so what is the Doppler effect? Wow. So write down what you think you remember about the Doppler effect. Now, I don't expect these responses are going to be as accurate as the other four because didn't do a very good job talking about it yesterday. So writing down a description of the Doppler effect. If you don't know, draw a picture.
Can we draw like what you drew yesterday?
If that's the Doppler effect, yes.
Oh, wait, what? Okay, wait, what you just said?
Yeah.
So let me, they just said like, Jamie like raindrop in Can I wash my hands?
Of course. There's a sip of water over at the sink. Who knows who Sheldon Cooper is?
Who?
Good.
What'd you say?
Do you know who Sheldon Cooper is?
Yes. Yeah, it really is. Yep.
Actually, I know the Wi-Fi thing, they need to make it.
All right, who wants to, hey, Tristan, put your back on. Who wants to, try and give an explanation of the Doppler effect? Sure, hold on, yes. Come draw it over here. While she's drawing, who wants to, give an explanation of it? Or try to? Anybody brave enough?
What did you say?
Doppler effect, can you give an explanation? Yeah. It does have to do with frequency change. Mhm.
Oh, okay.
Sure.
Isn't it like where you get a static on like television?
No? No. Doppler effect has something to do with moving and sound or light.
It's not something like that, like with raindrop down in the water. And
Uh,
the ripples.
Yeah, there are ripples. Mhm. There are waves going out. Hey, Alicia, the next time you look at Dominique, you should say olive juice.
Yeah.
It looks like you're saying I love you.
Oh,
That works too.
Or I love YouTube.
All right. Yeah, that's good. Praise God. All right, so I'm going to draw a bigger version of what she has here.
Who's trying to stable plastic?
Kind of.
It's a jade plant. All right, so here's something hitting a pond and the waves are spreading out, right? Okay, but when we're dealing with sound, it's quite a bit different. What's up?
Then my mom texted me.
Say what?
Then my mom texted me.
I know.
You think she's texting you?
Yeah.
Cool.
Can I check message?
No. When we get to the assignment, yes. So,
The assignment?
Yeah.
What is that? Oh.
all right.
No, it sounded weird. It sounded like I was saying what is the assignment, but I was saying what is the assignment.
Gotcha. So if the source of the sound is moving, then that causes there to be, that makes a change in the frequency of the sound that's being produced by that object. Oops, that didn't work. Okay, so we have the waves compressed here, we have the waves extended here, and that's what we're gonna see in this example. Okay, so what I want you to do is write down one thing you learned from this video.
Yes, sir.
Alicia, Alicia,
Is that the assignment?
Alicia.
Is that the assignment?
No.
It's a Doppler effect.
Okay, so they're gonna give us a Doppler effect, the technical version.
That's funny.
Oh, that reminds me. I got, from Owen, Dominique, Leslie, Lee, Tristan, Anna, Liz, Peyton, and Jacob. I have the letter from Leslie, Anna, Liz, and Tristan. So that means Olin, Dominique, Lee, Peyton, and Jacob still owe me letters.
Why it's disruptive talking fast.
Why it distracts me from teaching when you're talking when I'm trying to get instruction. So, you guys want to go ahead and grab a chair and go in the hall and write that half page, and then you can bring it back in. Yeah, so grab a chair, go in the hall. So, Olin, Dominique, Lee, Peyton, and Jacob.
What is it about?
The other day when you were disrupting class, I told you to write a half page, tell me why you shouldn't distract me during class. So, I agree. Just write a half page explaining why. Jacob, Peyton, let's go. Dominique, Lee. It'll be great. You need to write a full page to explain why distracting in class isn't a good idea.
Oh, alright.
Whole page.
You got some bigger?
Yeah, over in that drawer.
Mr. Sanders, should I go with you, because I was talking to you? I ain't gonna lie. So should I go right?
No, this was from 2 days ago.
Oh, I thought that was right.
Oh, no. This is from,
Right now.
no. This is from 2 days ago. I appreciate that though. That's really cool, man. That's really good. Okay, so let's try this again. So write down one thing you learned from the video.
In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source and the wave and the observer.
I saw that episode.
What was that?
Say that again.
That's the technical version, and don't worry, we're gonna simplify here in just a second.
in Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something
Anybody gonna have seizures? Okay, good.
like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up.
Okay, what does he mean, the wave fronts bunch up?
Okay,
What?
More compact.
What?
I write small,
Good.
so, can I just write a paragraph,
No.
He said it very good.
a full page?
Yeah.
You just said half page.
No, I told you a full page, because you had to ask me what was up. And I already said it 4 times.
What?
You should start listening.
I'm gonna write a full page.
Okay, so.
So dumb.
All right, so what does he mean by the waves are bunching up? Tell your neighbor, quick. What does he mean?
The more compacted.
Absolutely.
She just told me.
Hi. Okay? Good. Oh. All right, someone point to where the waves are more compacted. Pete. Come on, man. Hey, that's half page. Okay, go ahead. Point to it.
That way.
So on this side?
Yeah.
Yeah. Obviously, they're more compacted because they're closer together, right? Nothing wrong with that? I was just making sure it wasn't from out there. Yeah, so the waves are more compacted here. So what does that mean about the frequency? It's going to be higher frequency. Very good. Okay.
And behind it, they're spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency. And if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of the applications. So let's say you are standing in the middle of a
What are you
road.
doing?
That's you, and the car drives past
Oh,
you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As in some of its applications. So that is a
How'd you go from?
And if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and the car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a frequency, which you interpret as a high
How do we know that's higher frequency? Waves are close together.
pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also
Okay. So I want you to try and explain the Doppler effect to the people at, person immediately close to you. Explain what the Doppler effect is and how it works. Okay, just a short description of what you just saw. We'll watch it again if we need to.
It is.
Yeah, listen to my description. Yes, I am. I'm just not listening. That's so rude. Ooh.
Mr. Tyler, can I go to the bathroom?
Yeah, sign out on the board.
No, something's over there being rude. He's not doing it.
Say what?
Yeah.
Is he related way?
It's the change in frequency because of where the person is compared to the waves. Yes. All right, turn in the business science books, please, to page 234. And there's books over here. Don't have one. Seriously, there's more books. All right, so looking at page 234.
Mr. Taylor?
Yeah.
274.
234. Lizzie is back after Okay, now, what are some similarities that sound and light have? Yeah.
They have particles that travel.
They need particles, that's true, and light is actually tricky, but that's not what I'm looking for. What are some of the waves? They both have waves. Okay, so if they both have waves, brighter and lighter, what would that be? Think of these words here: amplitude, crest, frequency, and trough. What would lighter and brighter be? Amplitude would be brighter, that's right. So if you increase the amplitude, it's going to be brighter, right? So we increase the amplitude of the light in this room by having the lights fixed and having more of them on. Good. Okay, so the Doppler effect works with sound. What about with light? Okay, so what you need to do, and you can use the book, you can use each other. I need an explanation for how Doppler effect affects light. What happens to light is if you see it and it goes past you, even though you have to be able to detect it, you have that special instruments. So that's not the point. The point is, what happens or how does it work with light? You got the Doppler effect in sound. So what does it change when it comes to light? She's very good at tuning things out.
We're supposed to be writing down.
Yeah. All right, turn to page 230.
How to coach sound.
After Ed, who's after Liz, who's after Addison. Let me give you a hint on this. If we're talking about light, so when we were talking about sound, we were talking about changing frequency from the object coming towards you to the object going away from you. Change in frequency, right? So what's that mean when it comes to light? We hear we hear higher pitched sound. We hear a lower pitched sound on this side, higher pitched sound on this side. So if this was light, what would be the difference from front to back? Huh? Not brighter. Okay, so actually you're gonna need part of the next chapter. What chapter is that? 10. Yeah, you're gonna need a little bit in 11. Oh, you're there. Okay, you're fine and stuff. Good. So look, you'll need a little bit of what's going on in chapter 11, which I had, you guys did several on a while back. When it comes to the different light frequencies. Oh, your pencil. Why would you leave it over there?
I didn't think anyone would actually have the access.
Well, you know, what are we doing?
Whoever has my orange, I guess, can come back to that, because I know my mom.
Is that the one that Liz is holding?
It's like the orange. Oh, no, you know, that's why people like it. She's so big.
Okay, so use page 234 and 280. 248. Those two pages will help you explain what's going to happen with the light in the front, how's it going to change, and what happens with the light in the back. Okay? Remember, we're talking about frequency. All right, raise your hand. Raise your hand if you don't understand the question.
I don't even know what we're doing.
Okay. So can everyone else listen for a sec so I can explain the question again, because it wasn't worded well. I understand that. So previously this was a sound being emitted from an object that's moving this direction. We know that the sound in front has a higher frequency because the waves are closer together because of the movement of the sound. So now in the waves behind the sound were a lower frequency because they're farther apart, thus making a deeper sound on the backside. So what we want to do now is pretend this is an object emitting light. So we had a higher pitched sound here, we had a lower pitched sound here. What's going to be the difference when we're talking about light? What's going to happen here? what's gonna happen here? Okay, it's all about frequency, but what does that mean when it comes to light? Okay, so what happens here? What happens here? You got a question? If you use a combination of 234, 248, 252, it should help you significantly. Oh, turkey!
What were you saying? Oh, yeah, I said I couldn't pull it out. Nobody else.
Well, I don't know if I have that option right here. No, she's not taking it from her. She wasn't charging it. Yeah, so what's your answer?
The Doppler effect is the same sound all the time.
No, what about, we're talking about light. I just said it just now. You just asked what the question was. So here's light waves coming out from this object. How is this going to be different than this when it comes to frequency? We know this is higher frequency, but what does that mean for light? What does higher frequency mean when it comes to light? You're not using the picture. Huh? No, we're not comparing. We're not comparing. What's the frequency here? More space or yeah, so what does that mean?
Hey, Dominique, how did it go? What happened? Who did you say it to?
I was not even listening to it.
Mr. Taylor. You know, our bones are harder to steal for. What? Oh, I said, if the frequency is faster, the light would be brighter. If the frequency is slower, the light would be less bright. I'm not sure if that's right, but I mean, that's what this sponge means. Yeah, that's basically.
They can't see.
Yeah.
Look. Was it a love note? I never wrote her. Did you date him? That would be if you weren't already thinking.
All right,
Go ahead, Dominique.
I want to, leave your text back here, please. Okay, with all that talking, I assume that most of you had done a great job explaining that and talking about it with your neighbor. So the question is, how is light different on the front side of the object moving faster towards you compared to light on the back side moving away from you? Sure.
If the frequency is faster, the light will be brighter. If it's slower,
Okay, hold on. And you're not the first one to do this. Many of you are telling me the sound's gonna be louder as the car's moving towards you, or the light's gonna be brighter as it's moving towards you. It's not, what does bright and loud mean? That means amplitude. That means how big the wave is. But you said it yourself, Addison, you said the frequency is going to be louder. We're not talking about, or brighter. It's not, frequency isn't bright. What is frequency? Speed of the wave, size of the wave. So higher frequency with sound means higher pitch. Higher frequency with light means what? No, that's amplitude. Brighter is not frequency. Brighter is amplitude. So brighter means bigger waves. Frequency means faster waves. Hold on. Look at the book.
Will the distance be longer?
No. After it passes you, yes. Okay, look at page 252.
You get it right there.
To 52.
Can you interest the chair book?
Sure.
We can be book sharing.
Everybody on 282? Can you wait around my desk? Hopefully you're writing how much you love your mother. Okay, Jake. All right, on page 252, there's electromagnetic spectrum diagram thing there. What do you notice about the waves on the right side of the diagram? Higher frequency, which means closer together, which means faster. I would have heard that.
Exactly.
Oh, you're right.
Because she was trying to get me.
I know, man. What are you doing, girl?
She wanted to hit me with that.
I did not know that.
No, please just put it down. Okay. So on the right side, we see higher frequency, right? On the left side, what do you see?
Lower frequency.
Lower frequency, which means what? More space between the waves. But when it comes to light, we can see. What does that mean? Okay, what is white light made of? All the colors. How do you get a different color when it comes to? I know you know it. How do you know, or what makes red red and violet violet? Huh?
Filter.
But how do you do that with light? Filter. It's not mixing anything.
Take it away.
Guys, it's all. Okay, look at page 248. No. 250, right there. 250. There's a energy, color, wavelength, frequency.
Wavelength of the light.
250.
So the color depends on how much.
That could be the wavelength.
Hold on, Erica, say that again.
The color depends on how much energy.
How much energy, and how do we measure the energy? With frequency. The color depends on how many waves are coming and how fast those waves are coming. So longer waves is what color?
No.
Longer waves is red.
Red.
Shorter waves is what?
Violet.
Right. Okay, so let's try this again. If this is my light source emitting these light waves, the front side is going to be what color?
No.
Violet.
No.
Violet because it has a higher frequency.
Violet.
You guys agree with her?
I agree.
Or do you agree with Alicia?
Wait, what's she saying?
You're answering, but you don't know what she said. Okay. Hey. Higher frequency, it's going to be more violent. Violet. Lower frequency, more red. Okay? It says it right there in your book. So when objects are coming towards you at a very fast rate, they're going to be more violet. If they're moving away from you, they're going to be more red. Now, there's no way there's no way we can detect that, because the speed of those objects has to be pretty ridiculous to be able to see the difference. But not only that, you have to have special equipment to be able to see that difference. Okay, let me get the lights. Slow you down.
Did you order that for yourself?
Huh? I've had it for years. Hey, guys, what are you doing? About to, we ain't left yet. No. Put it back. Not there. Okay.
So that's another kind of way, line. So let's say you look out here at 11.3 and you see this.
Sit down, guys.
Just like they call sound waves, if the star is moving towards you even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is.
So if we see light at a higher frequency, what does that mean?
Right.
No, that's amplitude. Frequency, what does frequency mean with light?
You said if it's moving towards you, you see more.
Higher frequency, not amplitude.
Oh, okay.
Amplitude is bright on light. With sound, it's volume. Okay, so what do we see if it's moving faster towards us? What colors are we going to see?
You're gonna see like red.
You're going to see violet colors.
I thought that
Go back to page 250.
So I thought it was going the other way.
Frequency and sound is itch. So what does that mean?
I thought it was the outside.
Huh?
Part.
Oh, yeah, it'd be that there.
The light. Well, if we look at our handy pocket electromagnetic spectrum chart, you see that a small change in frequency for visible light will change this.
Okay, so this is low frequency, high frequency. So if it's moving at us with high frequency, you're going to see it be a little bit more violet. Away from us. Yeah. All right, Leah, you talk to me.
I'm here.